Okay, so here we have our review for physics. So we start off with AC circuits. And we've done a couple of these RLC circuits, but it kind of puts together everything that's involved. So what you have is some time varying current. So we'll say I of t is equal to 0.5 sine of 2 pi f t. So that's the frequency. The amplitude is 0.5. So based on that equation, we know that it's an AC signal. If it was DC, it would just be a constant value. And normally we'd have a voltage for DC circuits. Okay, then you have a resistive element. Now, just be warned, I may not do it in this order on the test, so you have to understand what things are. Don't just say, oh, this just looks like the test, because it isn't exactly the same. So just be careful, you know what's going on here. So this is the resistor, and we'll give that some value like 101 ohms. The inductance, we'll say it's 41 millihenries, and the capacitance is 35 microfarads. So you see we've got micro, milli, just plain old resistance. And the last thing I have to give you is a frequency, because we know that the frequency affects the behavior of AC circuits. So what can we say about this? Well, we know the resistance, which is the resistive reactance, is just 101 ohms. We know that the capacitive reactance is 1 over 2 pi f times the capacitor. So we're given the frequency, which is 110 hertz, and the capacitance is 35 times 10 to the minus 6 farads. So we have to convert microfarads to farads. And let's see what we get. 1 divided by 2 divided by pi divided by 110 divided by 35 e to the minus 6 power. So I get the capacitive reactance at 41.3 ohms. That's C, X sub C. And then we have the inductive reactance, which is equal to 2 pi f times L. So we have 2 pi times 110 hertz times L, which is 41 times 10 to the minus 3 henries. So we have to convert millihenries to henries. So 2 times pi times 110 times 41 e to the minus 3 power is 28.3 ohms. Make sure you're showing all these units. They're all ohms. Notice the frequency. We already wrote that down. Frequency is 110 hertz. And the amplitude. So, yeah, what is the amplitude? Well, in this case, the maximum current is 0.5 amps. So whatever this amplitude of the sine function is the maximum current, because this is current. So this is going to be, sine goes between -1 and +1. Okay, now you have to put all this together in terms of impedance. So the impedance is the square root of x sub r squared plus x sub L minus x sub C quantity squared. So my resistance is 101 ohms squared. Then we take x sub L, which is 28.3 ohms minus X sub C, which is 41.3 ohms. And I'm just going to double check, make sure that I am doing it in the right order. Always forget. So okay, impedance X sub L minus X sub C, so that's correct. Now, because these numbers aren't that big and the difference is even smaller, the actual impedance is not going to be that much different than the actual resistance, but that's just because I picked these numbers from my memory here, I just decided that's what they're going to be. So you get a 10,370, and if you take the square root of that, you'll get 101.8 ohms. So that's the impedance. So what does the impedance do for you? Well, you can use the modified Ohm's law, and that says that the current, or the voltage, is equal to the current times the resistance. Voltage is equal to current times resistance, but instead of using R, we use Z. And this applies for the maximum. So the maximum voltage is going to be equal to the maximum current times the impedance. And the RMS voltage is going to be equal to the RMS current times Z. So in this case, we're given the maximum current, which is 0.5. So we know that I max is 0.5 amps. Therefore, V max is just the maximum current times impedance. So 101.8 times 0.5 is 50.9 volts. And then to find the RMS values, all you have to do is divide by the square root of 2. So you take the maximum, divide by the square root of 2. So we got 0.5 amps divided by the square root of 2, which is 1.414. 0.5 divided by the square root of 2. So that's 0.354 amps. And likewise, the RMS current is equal to the maximum voltage divided by the square root of 2. That's because I times V is the power. So you get the power is half. So when you multiply 1 over the square root of 2 times 1 over the square root of 2, you get 1/2. Okay, so the maximum voltage we got from here, divide by the square root of 2. So 50.9 divided by the square root of 2. .0 volts. And the only other thing you have remaining is the phase angle. So the phase angle is the inverse tangent of X sub L minus X sub C divided by X sub R. And as long as your calculator is in degrees, you'll be fine. So we have 28.3 minus, I'm just looking here, 41.3. Same numbers you used to calculate the impedance, but you in this case you have X sub L minus X sub C over X sub R. So we take the inverse tangent of 28.3 minus 41.3, the whole thing divided by 101. And because this is negative, we're going to get a negative phase angle. And I didn't realize, yeah, I've got mine in, I did it in radians, so I've got to do it again. So you get phi is negative 7.3 degrees. And if you wanted to kind of represent this on a phasor diagram, you know, this is x sub L, this is x sub C, this is x sub R. So you'd have, in this case, this would be 101. X sub L was 23, so that'd be a short thing like that. X sub C goes this way, so that the net of these two is going to be about that long. And then you draw from here down to there, like that. And this would be the phase angle. So x sub R, x sub C, x sub L, add these two together. Whichever one's the longer, it'll go in that direction. Then use this difference to give you the y value, and use x sub R to give you the x value. Draw a resultant vector. Okay, so that covers a lot of stuff. The only other thing is light, is electromagnetic waves. So the only thing you have to know here is this relationship: speed of light is equal to the wavelength times the frequency. It's the same wave relationship. So C is equal to 3.0 times 10 to the 8th meters per second. And let's say I'll give you F. So let's say F is 100, let's say 1,000,000 hertz. Remember, light waves, actually I don't even know if this applies just to electromagnetic waves, so I don't know whether this frequency is in the visible spectrum. But you can still calculate lambda. Lambda, if you solve for lambda from this equation, it's just the speed of light divided by F. So we have 3.0 times 10 to the 8th. This is probably more like a radio wave. F is 1 times 10 to the 6th. So that 3 divided by 1 is 3. 10 to the 8th divided by 10 to the 6th, 10 to the 2nd. And the units are meters. 3, so that's about 300 meters. Yeah, so that's definitely a radio wave. I could also give you lambda, and you have to calculate frequency. So let's say it's 3.2 times 10 to the minus 12th meters. That's the wavelength. Again, C for light waves or any electromagnetic wave is 3 times 10 to the 8th meters per second. So if I solve for F, F is C over lambda. So you get 3.0 times 10 to the 8th meters per second divided by lambda, which is 3.2 times 10 to the minus 12th. So again, if you take 3 divided by 3.2, you get 0.938. And here you have 10 to the 8th divided by 10 to the negative 12th. So that's 10 to the 20th power. And that's hertz. I was just pausing there because I didn't know if that was, again, I don't know if that's realistic. I think the test numbers probably are more realistic. In this case, I would actually rewrite this as 9.38 times 10 to the 19th. So what I've done is taken 10 from here or multiplied this by 10, divide that by 10. And that way you've got a number between 1 and 10 in terms of scientific notation. Okay, so that's chapter 21. As far as, oh no, we've got one more, transformers. So remember, in a transformer, you've got a primary side, and it has N1 number of turns, and then you've got the secondary side. So I'm drawing more turns in the second loop. So this is N2. You have some kind of iron core. I'm just going to show it by kind of like that. And so, you know, one thing about transformers, it has to be AC, and the frequency is, you know, usually between 50 and 60 hertz. So in America it's 60 hertz, and Europe it's 50 hertz. You have to have enough of a variation so that you can generate enough magnetic rate of change of magnetic flux to get kind of the connection between the two coils. You also typically have an iron core. At those lower frequencies, you need an iron core to accentuate the magnetic field inside between the two. So what you have is you would have an RMS voltage going in here. Let's say RMS 1, and you have an RMS 1. So this is the primary side. And then you have an RMS 2 and an RMS 2. And the reason we're using RMS is because that's kind of the one that's important for things like transmitting energy, power. So we're going to just use RMS. Now, if you did max, it would apply as long as you were consistent. Maximum voltage, maximum current, maximum voltage, maximum current. So if you see this thing about RMS, it's just telling you that it has to be an AC signal for one thing, and that RMS is the important thing. So the relationships here are that V2 is equal to V1 times. Now the question is, which way does it go? So if the number of loops in the secondary coil are greater than the number of loops in the primary coil, you should have an increase in voltage. So it's going to be N2 over N1. So you could say V2 over N2 is equal to V1 over N1. And then you have this, for an ideal transformer, you have that V1, and I didn't write RMS in here, so I should. So let me do that. So VRMS 2 is equal to VRMS 1, which, remember, RMS stands for root mean square. And it's just taking the AC signal and converting it into a DC signal that has the same power consumption. Okay. And then you can, this conservation of energy across the transformer is VRMS1 times IRMS1. So voltage times current's power, VRMS2 IRMS2. So typically you're given 3 out of the 4, and you just have 3 out of the 5. So you can use this one to calculate the voltage, and once you have the voltage, you can calculate the current. So let's say N1 equals 200 turns. N2 is equal to 2,000 turns. And then we have VRMS1 is, let's say it's 0.05 volts, and IRMS1 is 0.5 amps. So you can calculate VRMS2 by taking VRMS1, which is 0.05 volts, times N2, which is 2,000, divided by 200. And so this is a ratio of 10, so it's going to become 0.5 volts for the final voltage. And IRMS2 is equal to IRMS1 times VRMS1 divided by VRMS2. So the current through the secondary coil, because you're increasing the voltage, the current has to become less. So we have 0.5 amps times RMS1, which is 0.05 volts, divided by VRMS2, which is 0.5 volts. So this increased it by a factor of 10. This decreases it by a factor of 10. So you get 0.05 amps. Okay, so that's how transformers work. Okay, that is chapter 21. Now, there's going to be two problems. One's going to be a calorimeter problem. Actually, the three problems. There's a calorimeter problem, there's a specific heat problem, and there's going to be an insulation problem. So let's start with the specific heat problem. This is asking you how much energy it is required to increase something from one temperature to another. So I'm going to give you all the specific heats. It's going to involve water. I'm going to give all the specific heats and the heat of fusion and the heat of vaporization. So let's say, let's say our initial T1 is 32 degrees C, and the final temperature is 301 degrees C. Now what you have in the middle here is boiling. Now you should also be able to handle freezing or melting and boiling, one or the other. So it's going to be freezing to solid water to liquid water with a melting. You can go from liquid water to steam and the corresponding phase change there, or I could start at ice and walk all the way up to steam. So those are the three possibilities. Now here, this is liquid because it's between 0 and 100, and this is gas. So the total amount of energy, and this is energy, so this is in joules. And so it's going to be made up of three parts here. So you're going to have, so the total heat added is equal to the mass of the material times the specific heat of, I'll put LW, liquid water, times delta T, plus the mass times the latent heat of vaporization for water, plus the mass, again, they're all multiplied by the mass, times the specific heat of steam times delta T. And this delta T here is from 32 to 100, and this delta T is from 100 to 301. So all I have to do here is plug in the numbers. Let's say I have 2.5 kilograms. So that's mass. I have to give you the mass. I'll give you the initial final temperature. If it's less than 0, it's a solid. If it's greater than 100, it's a gas. If it's between 0 and 100, it's a liquid. So in our case, we have 2.5 kilograms. Again, I'll give you the specific heat of water, which turns out to be 4186 joules per kilogram Kelvin. And the temperature difference is 100, which is a boiling point, minus 32 degrees C. It's not 30 degrees Fahrenheit, degrees C. So that's to heat the water up from 32 to 100. Then you got the same mass times the latent heat of vaporization, which is 2.26 times 10 to the 6th joules per kilogram. And then finally, same mass, 2.5 kilograms times the specific heat for steam, which is 2010. So that's joules per kilogram Kelvin. And the temperature goes up to 301 from 100 degrees C. Now here it says K and here it says C, but changes in those are the same. So here it's not where the absolute temperature makes a difference. It's the change in temperature. So let's go ahead and calculate each one of these, and then we'll just to see what the order of magnitude is. Okay, 711,600 joules. So that's heating it up. 2.5 times 2.26 e to the sixth. So the vaporization takes 565,000 joules. And then the last part here is the steam. So you have 2.5 times 2010 times 301 minus 100. And that comes out to be 101, well, 101,000. So it's a little over a million. So this was a 700,000, so it's 5 million. So you just add those three together. And usually if you have boiling or any phase change, those are pretty significant amounts of energy. So I get 6,460,000. Go round it off here. Joules, which would be equal to 6.46 megajoules, because I've got 10 to the 6. Okay, so that's easy. The next one is a specific heat, and we did a problem in class. You basically have a certain amount of water. This is a calorimeter, so you got a calorimeter that's insulated. You got a certain amount of water in there, so that's H2O. You have some kind of hot thing. So this has a mass. I'll say the mass, we'll just call it M. And let's say that's 4 kilograms. We'll say the mass of the water. You have to give the mass of the water, which is going to be 10 kilograms. Say that the initial temperature, so let's put a W for water, mass of the water. This is the mass of the object. The initial temperature for the water is 25 degrees C. And we need the specific heat. Specific heat of water is 4186 joules per kilogram Kelvin. And we did this two ways in class. So either way's game here for the test. So I can either give you the specific heat of this and the initial temperature of this, and you can calculate the temperature rise, or I can give you the temperature rise and you can calculate the specific heat. I mean, there are other options, but those are the most likely. So I think I'm going to give you the initial temperature here, which is 400 degrees C. The specific heat of this object I'm going to say is 701 joules per kilogram Kelvin. So if we were to write this out, the decrease in energy through heat transfer here is going to be balanced by the increase. So you basically have the mass of, let me just do in different colors here. You have the red stuff. So you've got the mass times the specific heat times T final minus T initial, MC delta T. Then you add the blue stuff. It's mass of the water, specific heat of the water, T final minus T initial for the water, and those added together have to be 0. So this final temperature will be lower and this final temperature will be higher. So you have a minus and you have a plus, and they balance each other out. So let's go ahead and plug the numbers in. Make sure I gave you everything. 4 kilograms, 4186, T final minus T initial, plus the mass of the water, which is 10 kilograms times specific heat for water. So I mix those up. Let's go fix that. So this is specific heat, there's 701 And I've got those mixed up too here. This is the original. So let me just make sure I'm doing it right here. So this is for the object, mass of the object, specific heat of the object, initial temperature of the object, 400 degrees C. Then we have the mass of the water, specific heat of the water, T final minus T initial equals 0. So you're going to multiply these two numbers together. 4 times 701. So you get, sorry, just push the button for my tablet. Okay, so you get 2,804 T sub F, these three things together. And then you multiply 4 times 701 times 400. So that's minus 1121600. Then we have 10 times 4186. So that's 41,860 T sub F minus 10 times 4186 times 25. So then you get negative 104,36500 equals 0. So add these two together, 2804 plus 41,860. So that's 44,664 T sub F. If you add these two together and put them on the other side, 1121600 plus 1046500, you get 2,168,100, and then divide both sides by 44,640. 664. And it should be greater than 25 and less than 400. And you get the final temperature is 48.5 degrees C. And again, because we're dealing with temperature differences, you do not have to convert to Kelvin. Again, the other option is I could give you the final temperature and you could calculate the unknown specific heat. And then you've got the heat transfer calculation. So it all comes down to a few things. One is that heat transfer is equal to area times T, I'll say in minus T out, divided by R, where R is the summation of the R values, R sub I, however many layers you have. So you just add those together. You know, A is the cross-sectional area. It's going to be meters squared. And again, because we're dealing with temperature difference, it doesn't matter whether we use Kelvin or C, and most likely we're going to be dealing with degrees C. Also remember that R is equal to L over K. So I could give you K, and if I gave you K and L, you could calculate R. Or I might just give you R. I give you R. If you had R and L, you could calculate K. So, you know, that's, and this is not resistance. This is R value. This is length. This is heat transfer coefficient. So let's say I give you a composite wall of some kind. So I'm going to make it. And I'm not going to give you exactly this composition. You spell styrofoam. This is a 2x4 wall, and this is sheathing, and then we got another layer on the outside, which is we'll call it shingles. So I'm going to give you a list of R values for all these different kinds of things. So, and I'm going to give you them in SI units. So let's see what we have. We have styrofoam, and I look on my, so this is styrofoam. I don't say how thick it is, so it's going to be whatever. It's probably an inch thick. And you have an R value of 0.88. Now these don't correspond to the R values that we did in class, because those were English units. These are SI units, and the units are meter squared, degrees C, seconds per joule. The R values, like an R value 6, is going to be feet squared, degree Fahrenheit, seconds per BTU or something like that. So don't worry if those don't look like something you've seen before. Then I see something that says 3.5 inch fiberglass batting. So what that is that's going to be the wall. So this 2x4 wall, we're going to put, it's a 4-inch wall, we'll put 3.5 inches of insulation in there. Okay, R value is equal to 1.92. Again, you'll have this table, but you'll be able to get this stuff off however I decide to put it together. Then you've got sheathing. Sheathing, again, sheathing is usually a certain thickness. And the R value for sheathing is 0.23 meters squared, degrees C, seconds per joule. And the last thing is shingles. So they've got wood shingles. So if you just wonder which one am I, if you get confused about which one's which, you can just come and I'll talk. I can explain it to you. Hopefully you won't have that problem. Okay, so this is what this whole thing consists of. So what you do is you do the total R value and you just add them together. 0.88 plus 1.92 plus 0.23 plus 0.15. And that's the beauty of R value. You just add the numbers together. So 0.88 plus 1.92 plus 0.23 plus 0.15. That gives you a total of 3.18 meters squared, degrees C, seconds per joule. And let's say it's a 3.0 meter by 5.6 meter wall. So I have to give you the dimensions. So the area would just be 3 times 5.6. So that's 16.8 meters squared. And I have to give you inside temperature and outside temperature. So the inside temperature we're going to assume is cold, is warmer. So let's say it's 25 degrees C, and the outside temperature is 5 degrees C. So we have everything. We have our total R value, our area, our temperature difference. And remember this equation, which I'm not sure if I did this right. Yeah, this is heat transfer rate. So go back and fix that. So that's joules per second. So Q dot is equal to the area, which is 16.8 meters squared times the temperature difference, which is 25 degrees C minus 5 degrees C divided by the R value, which is 3.18 meters squared, degrees C, seconds per joule. Let me just multiply those together. 16.8 times 20. 25 minus 5 is 20, divided by 3.18, and that gives me 106 joules per second, because that's energy per unit second. Now, if I said how much heat in joules is lost in 6.3 hours. So to do that, you just say the heat transfer is equal to the heat transfer rate times the time. So it's joules per second times seconds. So you can see I need to take 106 joules per second and multiply it by 6.3 hours. But then you've got to convert that to seconds. So it's 60 minutes per hour. And pull it over here, times 60 seconds per minute. You see that cancels out with that, pencil cancels out with that, that cancels out with that, and you get 106 times 6.3 times 60 times 60, which is 2,400,000 joules. So that's how you calculate heat transfer from heat transfer rate, as long as you assume everything's constant, temperature difference constant. One last thing I may ask you to do is, let's say, for the wall, where's the wall back here? Yeah, the wall. What if I asked you to, what is the heat transfer coefficient associated with an R value? So remember, R is equal to L divided by K, or K is L divided by R. So in this case, I've got 3.5 inches of insulation. Now, of course, I've got to convert that to meters because R is in meters squared. So I'd have to multiply by, let's see, so it's, I think I'd divide by 2.5 centimeters. Actually, I'm going to multiply by 2.54 centimeters. So you'd have 2.54 centimeters per inch. See how this cancels out? And then I would need to convert centimeters to meters. So that's going to be 100 centimeters per 1 meter. And then I divide by the R value, which is 1.92 meters squared degrees C seconds per joule. So let's see what we get. 3.5 times 2.54 divided by 100 divided by 1.92, and I get K is equal to 0.0463. Now the units, you can see this meter is going to cancel out with one of those, but then you take the reciprocal, so you get joules per meter degrees C second. So that's the units for K. So that I may ask you to do that. Take one of these R values with a dimension L, which may be in inches, convert inches to meters, and then do that. Okay, so that's the heat transfer type calculation. Now we're moving on to chapter 13. So I think we got two problems there. We got a spring mass system and a string, waves on a string problem. So, with the case of a spring mass system, it doesn't matter whether this thing is hanging vertically or whether it's in space and going sideways with no friction. The key thing here is that you've got one end's fixed, the other end's moving, and this thing's going to oscillate up and down. And the key thing is that, in this case, y as a function of t is going to be some y max times the sine of 2 pi ft. But for this case, for the case of a spring mass system, it's equal to the square root of k over m. So this is kind of using the fact that omega, the circular frequency, is equal to 2 pi f, and also that omega equals the square root of k over m. Also, the period is equal to 1 over the frequency. So what I'm going to ask you to do is I can give you, let's just give you an example. So here's given. Mass equals 3 grams. K is equal to 1.2 newtons per meter, because this is force per unit length stretched. And so what I can ask you to do is calculate what is the frequency and period of this combination. So you get 2 pi f is equal to the square root of k over m. So you get square root of k over m. K is 1.2. You'd have to convert grams to kilograms. So you'd multiply 3 grams by 10 to the minus 3. This is newtons per meter. This is kilograms. So let's plug those in there. 1.2 divided by 3 e to the minus 3. So that's the square root of 400. And the square root of 400 is 20. And that would be, cycles per second. If you do the units, it'll end up with 1 over seconds. So that's equal to 2 pi f, or f is equal to 20 divided by 2 pi. Now 2 pi doesn't have a unit, so you're still with cycles per second, oscillations per second. So 20 divided by 2 divided by pi is 3.2 cycles per second, which is hertz. So make sure you use hertz. And then T is 1 over frequency. So you get 1 over 3.2 hertz. 1 divided by 3.2 is 0.31. 0.31 time, period is time. So it's seconds. Now, then I might ask the question, by how much do I need to increase the mass to increase the period to 1 second? So here it's 0.3 seconds. So I need to get it longer. What do I need to do? Well, if the spring constant is fixed, then I have to increase the mass. So the question is, how high does the mass have to be? So you basically work your way back. So I know T is equal to 1 second. Therefore, the frequency is 1 over T, which is 0.33 hertz. So 1 over 3. Actually, that's not true. I don't know where I got 3 from. So you get 1 over 1. So that's 1 hertz, 1 cycle per second. Okay. Now, we know that 2 pi times the frequency is equal to the square root of k, which is 1.2 newtons per meter, divided by the mass. So now I can solve for the mass. So you square both sides. So you get 4 times pi squared times 1. So you get, the left-hand side becomes, so you're squaring this again. So you get 4 times pi squared, which is 39.48. And here you get 1.2 newtons per meter divided by m. So m is 1.2 newtons per meter divided by 39.48 hertz squared. Seconds inverse second squared. So you get 1.2 divided by 39.48, and I get 0.0304, which is 30 grams. How does that compare with my initial mass here? 3 grams, 30 grams. Yeah, I think that makes sense. So you've increased it by a factor of 10 in terms of the mass, but really you have to take the square root of that. So if you take the ratios of the square roots of this thing, you should work out correctly. So that's kind of the spring mass system, is I give you enough to calculate the frequency of the period, then I change either the spring constant or the mass, and then ask you what is the new, if I say, what do I need to change it to? Now, one little tricky part there, which I forgot to mention, is this is the mass, so the actual change in mass is the increase. So it's not this final value. You have to take this final value and subtract the initial value. So the actual increase is 27 grams. Final value is 30, but the increase is 27 grams. So when I ask you for increase, make sure you take that difference. And then the final problem is just waves on a string. And the relationships are that the wave speed is equal to the wavelength times the frequency. Okay, that applies to any kind of wave. You've got the wave speed is equal to the square root of f over mu. So f is the tension, and it has to be units of newtons. Mu is the mass per unit length, and it has to be kilograms per meter. So if I gave you a mass per unit length in grams per centimeter or something like that, you have to make sure of units. So I'll write this out, units. Make sure you get the units right here. And then the fundamental frequency is equal to the speed divided by 2L, where L is the length of the string, and that's also in meters. So I'm underlining those because I may just change. I may put the length in centimeters. I may put the mass per unit length in grams per meter, grams per centimeter. Who knows what I'll come up with. So the kind of problem that you would have is I will given is F and mu. Make sure the units are correct. You can calculate V, given F and mu, calculate V. This is meters per second. And then from that, you can calculate F1. Take the velocity divided by 2L. And then the harmonics are just multiples of the fundamental frequency. So for a string, it's like a tube open at both ends. You just take the fundamental frequency and multiply by the numbers here. So they double at first, but they go in integer multiples of the fundamental frequency. So theoretically, I could, the other option is I could what else I could do is I could give you L and the mass per unit length and the fundamental frequency, and then you could calculate, given that, you could calculate the speed, meters per second, and then from that you could calculate F equals, well, I said V was equal to the square root of F over mu. So that would be, if you squared things, you get v squared is equal to f over mu, or f is equal to mu times v squared. So that way you can figure out what tension you need for a given weight string. So there could be, different things I could give you, but the basic things you have to be worried, the equations, wave speed equals wavelength times frequency. Remember, the wavelength is related to the length of the string for the harmonics, and the fundamental one is always v over 2L because the wavelength is 2L for the fundamental frequency. Just make sure you think about the units here. I'll probably, I'll just ask for the tension in newtons. I won't give you kilonewtons or something like that. So this one's probably going to be in newtons. This will be could be anything, grams per meter, kilograms per centimeter. But once you've gotten the units in kilograms per meter, you'll be fine. Then you can calculate V. V is equal to the square root of F over mu. Once you have V and you know L, you can calculate the fundamental frequency. Once you have the fundamental frequency, you can calculate the harmonics. So you can see these are really, we don't use this one. It's really comes, this one is really that one. So there's really only two equations to get the fundamental frequency, and then these apply no matter what. Okay, so that's it. Pretty sure. Just click through here again, see if there's anything I forgot to tell you. Nope. Okay.